Okay, so let's start. So quick announcements, as you all know, homework 2 is due tomorrow, and tomorrow night. Hopefully all of you are in good shape with respect to that. Okay, and homework 1 grades were posted on Tuesday, and last night I posted solutions to the homework also. They're not complete solutions for some of the problems, they're more like, they should be enough to tell you what the solution is. So, that's about homework 1. Right, so any thoughts, questions? Right, so what's the plan for today? So today I want to complete what we started last class, which is talking about flows and cuts and graphs. Again, we're going to see a few applications of this, and we'll see something that we advertised last time, which we call the max flow min cut theorem. Okay, so this is a nice structural theorem that's an example of what is called duality, which we will see in the coming lectures. So let's start with a quick recap. Okay, so we defined this problem called the ST cut problem, the min ST cut. We said there are many variants of cut problems, and this is one version that happens to be solvable in polynomial time. And so the problem is the following: you're given a directed graph with edge weights. And what you want to find is a small set of weighted edges to cut so that there is no longer a directed path from S to T. Okay? So note that you are allowed to have, the cut can leave paths from T to S. You just don't want a path going from S to T. This is called the min ST cut problem. Right? And yeah, as I said last time, this arose because of some military applications where you want to disconnect places and by blowing up bridges and so on. Okay, so it has, we'll see an application of computer vision and places like this today. It has a bunch of nice applications. And we said that this is a problem that is solved, the algorithm for this problem somehow is obtained by not trying to solve this problem but something else. Okay, and this is one of the first examples we will see of that. Okay, and that's the reason I do this algorithm in class. So, and what is the other problem? So this problem is called the maximum flow problem. Okay. And this is more approachable. Okay, so the problem is this. You're given a directed graph. And now think of edges as capacities. Okay, we said that you can think of these as like the bandwidth of an edge in a network. That's what we mean by capacities. And the maximum flow problem is the following. So you're given these capacities CE. You are again given a source and a sink. And your goal is to send as much flow as possible without violating these capacities. Okay, so I'll show you an example in a little bit, but this is how we define this problem. Okay? So if you're still in this network bandwidth scenario, the CE of an edge is the amount of bandwidth it can support, And now you are given an S and T, and you want to see how much total bandwidth you can obtain going from S to T. Okay. This is the maximum throughput in some sense that you can achieve. And that is what is defined as the maximum flow. And we've defined this a little bit intuitively last time using a collection of paths. Okay, and one of the motivations we gave was maximizing the throughput of communicating between S and T in a graph. So, alright, so one simple example of this could be, we saw a graph like this. Okay. Right, so here we said that these are the numbers here denote the capacities, and let's say my S is this and T is this. Note that you are allowed to have back edges as well if you want. So you could have a graph that looked like this. There's no guarantee that edges only go from S to T or anything. Okay, so this is an example of a network where every edge comes with some capacity. Now, what is the max? Suppose you want to send information from S to T. What is the maximum throughput you can achieve in this network? Right. So you can say first I'll start off by sending some flow along this path. Right. So along the path that goes like this. Okay. And how much flow can you send along this path? 10, because you can't send more than 10 on that edge. So let's say you send 10 units of flow. Okay. And let's say I send some more flow along the bottom path. Again, you can only send 10. And now you'll notice that there is a bit more capacity left, right? Because you could in some sense, you've used this 10 and 10 of this, and you've used 10 of that and that 10. Okay? So you still have a path that goes diagonally, that goes like this. So okay, you can still route 10 units of flow along this path. Okay? And you can route 10 more units along that path. So this gives a total flow value of 30. Okay, so last time saw an example with a little bit different numbers. Okay, but it turns out this graph helps illustrate the things I want to illustrate better. Okay, so I change the weights. Okay, so this is so your flow in this graph. So the value of the sum of all those flow paths, which we will call the total flow that you are routing now. Okay, so that is 30. Okay, so the total flow value is 30. And now that this is how we define a flow. It's a collection of paths. There's a different way you can define flow, which is basically you can define the flow on every edge, and you want them to satisfy some conservation properties. Okay, but it turns out the two definitions are equivalent, and this is simpler, so we'll go with this. Okay, so a flow is simply a collection of paths. Yeah.
Why is the middle flow 10 when the total is 20 going across the whole? You go 20, 20, 20, but then it's labeled as 10.
No, so each path is taking 10 units of flow. Okay, and you can't increase it because if you send more than 10 each along the blue and the orange path, then the capacity of this edge would get violated, the top edge, because it was only 20, right? So you can, so this is what we mean by the capacity. So to respect the capacity constraint, the total flow which is like coming from all the paths that use the edge. On any edge E must be less than to the C sub E. So this is what the capacity constraint means. Okay, that you use a bunch of paths, okay, and the total flow that is going through any single edge, okay, which is the sum of all the path weights that use it, okay, must be less than or equal to the capacity. Okay, so this corresponds to intuitively what you feel. If you're thinking of routing a flow by a bunch of paths, you want the number of paths that use this edge or the weight of those paths to be less than or equal to the capacity. Okay. Yeah, so good that you clarified that. And this is again something I mentioned last time. So can you route more than 30 units of flow from S to T in this graph? No, and why is that? Any one person? Okay.
The maximum outgoing flow from the sink is 30, so you can't send more than that.
Yeah, so S is called the source, by the way. So the total outgoing capacity out of the source is 20 plus 10, which is only 30. So you can't send more than 30 units of flow out of S anyway. Okay, and so yeah.
But that is true for the target as well, right?
In this case, it's true for the target as well. Yeah.
But it is restricted by the source.
I mean, you could argue it in this case even from the point of view of the target. You could say that the target does not accept cannot accept more than 30, so you cannot have a flow of more than 30. Yeah, and sometimes we will see examples where it's not the source of the target that restricted, but there will be some cut which will be small. Okay, so this is how we define this. And last class we also started looking at a relationship between these two quantities, right? So one is the flow in a graph between S and T. The other is the cut value, which is the number of edges you've got to remove so that there is no path from S to T. Okay? And we said that we saw one very simple argument which said that the maximum flow is always smaller than or equal to the minimum cut. Okay? And we showed this by a very simple argument, the sequence of steps. So let's go through these one by one. Okay? So what we said is take any flow, right? A flow is just a collection of paths. I want to argue that so there is S, there is T, there's some flow like this, maybe it uses some common edges. Okay, this might look complicated, so we can use something like this. Okay, so this is a flow, right? So it can look complicated in general, right? Like the paths can all intersect edges and so forth. Okay? So the only condition you have is that if you look at all the flows that use a particular edge, the sum of their values is less than or equal to the capacity of that. This is the only thing you know about these flows. Alright, so I want to take the flow that maximizes this way. So this is the maximum flow between S and T. And now let's take any cut. Okay, a cut is a collection of edges. Okay. Whose removal disconnects S from T. Okay. So this is the definition of the cut. Right? So it's a collection of edges. So in this example, one set of edges that disconnects S from T is, let's say, this with this and this. This is a cut because it disconnects that. If you remove those edges, there is no more a path from S to B. So you could also have a more slightly non-trivial cut where maybe you remove this, remove this. This is a bad cut in the sense that you have cut the total edges that you've cut sum up to 60. Okay, so this is a pretty bad cut. Yeah, but it's still a valid cut between S and T. If you remove these edges, there is no longer a path. Okay, so right. So let's take any cut which I will call C. So what we argued last time is that you take this cut, and for every edge in this cut, look at all the flows that use this edge. Okay? We know that all these flow paths that use this edge. Okay? Now, what we know is that the sum of all those flow values, okay, is smaller than or equal to the cost of this edge, okay, the capacity of this edge. Right? Because that's the capacity of the edge. So you can't, all the flow paths have to add up less than or equal to the capacity. And now let's think of first removing all of that. Okay, so let's say this is my edge in the cut. I have removed this, I have removed this. Okay. I do this for every edge one by one. Okay. So the total amount of flow I have removed in this process is at most the sum of these edge widths, because each time the amount of flow I am removing is at most C sum up. Okay? Because I just argued that the sum of the flows that use this edge is at most CE. Okay? So if I remove that, I've removed at most CE units of flow. Okay? And so if I remove all of these, then CE prime, then I've just removed the total flow I have removed is at most the sum of these CE values. Okay. Now I want to argue that if I've removed the flows that go along each of these edges, then I've removed all the flow paths. Why is that? Suppose I delete all these edges and there is still a flow path. What does it mean? Yeah, so it means that the C was not a cut to start with. Okay? So if you take any cut, you know that every flow path must use some edge of this cut. So it must have been. Okay? And that's the whole argument. Okay, so for each edge in this cut, if you remove all the flows that go through this edge, you remove the total flow of at most C7B, sum this over all edges, and you get what you want. Okay, so this shows that if I take any cut, the value of the cut is bigger than or equal to the max flow. Okay? So I can now use the min cut, and I can conclude that the minimum cut is bigger than or equal to the max. Okay? So this is the argument that we've seen last time. So one non-trivial consequence of this is the following. Okay, so this gives you a way to certify that a cut is maximal. Okay, so this is something that you will see. It's one of the cool things in in a little bit more advanced algorithm design. You want ways of certifying that your solution is either optimum or close to optimum. Okay? Now suppose I gave you a flow, okay, any flow, and I gave you a cut, which could be any cut in the graph, with the property that these two are equal. That the flow value, that the total flow value is equal to the value of the cut. Then I automatically know that this flow was optimal. Okay? Because there was a cut that's equal to this, and this theorem already tells you that you're optimal. Okay? So this is you call these certificates in complexity So a cut can certify the optimality of a flow. Okay, and this is often quite uncommon, right? So usually the proof of so usually in all the algorithms we've seen so far, we would give an algorithm and we would prove that the procedure always computes the optimum value. So if somebody gave you just the final solution, right? So let's take a spanning tree, right? Somebody just gave you some spanning tree and they told you this was minimum, right? So how do you certify that this is minimum, right? So you have to do some computation to do this. But in this case, such a certificate is very easy to give. All they have to do is just say, hey, here's a flow in the graph. You can verify that this is a flow. It respects all capacities. Okay? And then they could just say, here's a cut, and its value happens to be equal to the value of the flow. Okay? Then you're already sure that this is optimal flow. Okay, so this is a very nice, so a cut can certify the optimality of the flow. Okay. So now you should be asking, can every maximum flow have a certificate like this? Okay, and that's what we will prove today. That's what's called the max flow min cut here. Okay, like any maximum flow has a certificate of this. So, all right. So that's this. All right. So now what we'll see is an algorithm for the flow problem. Okay. And I will demonstrate this paradigm by showing its proof of correctness by constructing a cut. Okay. And then it will illustrate what I just said now. Okay, so what is the algorithm that we want to see for flow? Okay. So the algorithm is, so the first algorithm I will present, this is what we saw kind of said last time, but I didn't have a good example. The example I had last time didn't work out. Right, so what you can say is a trivial algorithm which each time it just finds some path, okay, and it tries to route flow along that path. Okay. And once you do that, you increment the capacities or you change the capacities so that you've removed what you've used. Okay. So for instance, if I chose to send, suppose the first path I found was this, and I chose to send 10 units of flow there. This is exactly what we'd done some time ago, a couple of slides ago. It is send 10 units of flow. And now I know that this has no more capacity, so this capacity I will change it to 0. And I know that this guy now has a remaining capacity of 10. So it has some remaining capacity of 10. Okay, and now I observe that I can use this path, and I can route 10 units of flow on it. And then I can change the capacity of this to 10 and this to 0. And now I observe that there is yet another path that I can use. And I can send 10. And at this point, this guy becomes 0, this guy becomes 10, and this guy becomes 0. So there's no more capacity left. At this point, there is no path from S to T. Okay, so you stop. So in this case, it was great. You found the true maximum flow from S to T. Always this was S. Okay, so this is a natural algorithm that you can come up with, right? So you take some path and reduce capacities along that path, and now look in the remaining graph, see if you can add more flow. Okay, so this is kind of a iterative augmentation, if you like to call it. Okay, so you start with some flow, you augment it into. So, okay. But it turns out that this is not always. Actually, any questions? So I'm not telling you how you find these paths and so forth, right? I'm just saying find some path. No. Alright, so we'll see that this does not always do well. Okay, so here is a bad order for the same graph. Okay, so suppose I started out with a flow which did this. Okay, so which did 20. Okay, so perhaps I was greedy to start with. Maybe instead of sending 10 units of flow, I want to send 20 units of flow. Okay, so I did this, and maybe we sent 20 units of flow to start with here. Now what happens, right? So now this capacity is reduced to 0. This capacity is reduced to 0. And this capacity is also reduced to 0. And now you observe that there is no path going from S to T anymore in this new graph. Right? Because if you went here, then this edge now has 0 capacity. So somehow you made a mistake by using out all the edge capacity out here. Right? So this can be a problem. And on bigger networks, usually these kind of problems are at a much worse scale. Okay. So the moral of this is that you can get stuck at non-optimal loop. Because you've only used 20 units, so you've only sent 20 units of flow and you're already stuck, right? You know that the optimum was 30. So how do you, I mean, in some sense, it would be nice if you could correct such mistakes, right? And as I was saying, this is one of the few problems for which such a thing turns out to be possible. Okay, so, and this is the main idea behind what is called the Ford-Fulkerson algorithm. Where if you made a mistake of this kind, you can actually go back and correct it. Okay? I'll show you how, but actually, is this example clear? That you actually get stuck. If this green path was the first one you chose, then after this you can't make any more things. All right. So yeah, so this is what I was saying. So the main idea is, can you repair bad choices? And this is somewhat similar to backtracking. So let's see how this is done. But yeah, so any questions before we move on?
So
Yeah.
you say that 30 units of capacity of
Flow.
flow from the source to the target. It means that you can send that flow 30 at the same time.
Yes, that's how you should think of. Yeah, that's the throughput in some sense, right? That is, yeah, this is like, you can think of it as at steady state you are sending 30 units per second. Some paths may be longer than the others, so initially maybe some paths will take longer to get to the same. But at steady state you are sending 30 units. Yeah. So this is why it makes sense makes total sense in a network setting. I was worried for a while that this might not work because these pens are very fragile. It fell this morning. Okay, so this is the main idea. Okay, so let me introduce, and the idea is you want to repair these bad choices, and they do so by introducing what is called the residual graph. Okay, so this is the main idea is if you are given some flow F, okay, so given the current flow, so this is similar to this iterative addition algorithm. Okay, so at every step you have some flow that you've routed so far, and the idea is to define a slightly different graph, not just the kind of graph we defined earlier where you reduce the capacities, but you allow, in some sense, correcting for the choices you've made. Okay, so and that's captured to what's called the residual graph. And the idea is to then find the flow in this residual graph. It's similar to what we've done before. Okay, so let me see an example of. Let me show an example of this. So this was our original graph, and this was the bad flow. Right. So this was the F. Okay, so this may actually have caused. This does not have. So let's try once more. It will take 30 seconds. It's supposed to give about 20, 30 minutes. But yeah. Otherwise, we'll have to move the board. So the previous instructor to leave stuff on the board. So actually, does anyone happen to have an extra one of these things? Apple pen? No. Oh, you have one? I might ask you. Okay? Yeah, thanks. Okay, so this is my F. We used to work for a little while. Okay, so this is my F, and the residual graph is one in which you have something similar to what the original, what this iterative addition type algorithm did, where you replace, let's say, let's give these things names. So I have S, I have P, I have U, and V. Okay. So this SU edge, I'm going to replace with an edge of capacity 0 because it has capacity 0, and I start off with that, right? So this is capacity of 10, this is capacity of 0, this is capacity of 10. Okay, so I will need oh. Time is fast in order. can't use this either. So let me just use the board. I'll just fix this afterwards. Okay, so hopefully this can capture the board reasonably.
I think so, yeah.
I'm going to leave yours here just to distinguish. You know which side of this to use. Both seem to work well. Both have their problems, both have their. Yes, you remember? Okay, that was fine. Okay, so I wanted to just.
You'll
draw
have
this-
to write a little bigger.
Yeah, I'll write it bigger. Okay, so I wanted to draw the original graph, which was this. And yeah, so this goes. Okay, one can't see this, I guess, but okay, so this is 20 again. Okay, and there was this edge that was 20. Okay, so this is the original graph, and we have routed a flow which was something of this kind, which had 20 units. Oh yes. Is that better? Yeah. All right. So this is the graph, and this dotted thing is my flow. All right. So just to clarify, so this thing of 20, this is my f. Now the residual is defined, I will call it G sub f. And this is a graph where you have the same vertices. And now first you start off with what you did originally. So this gets 0, this gets 0, this gets 0. Okay, so this is what you have. Now additionally, you put backward edges wherever you've routed flow. Okay? And the backward edges have capacity equal to the amount of flow you've routed on that edge. So this would be 20, and this would be 20. Okay? So you add backward edges. given a graph G and a flow F, G sub F is defined such capacity of edge E is simply the original. So this is the new capacity, so I'm denoted by C new. Okay, this is the original C minus the flow on that edge. By flow on an edge, I mean the sum of all the weights of the flow paths that use that edge. Right? So it's the total flow that this original F was putting on it. Okay, so these are the forward edges. These were what existed in the original graph. So this is for the forward edges, for what I call forward edges. That is the original edge. That in this case, that's 0 and these things. Apart from this, we have backward edges. Edges with capacity C nu equal to the flow. Okay. So this is the formal definition. This is a generalized version of that picture. Okay, so in that picture I drew this thing for the specific F and for the G that we started with. So now you should be asking yourself, or you should be asking me a bunch of questions. What if the backward edge had also existed in the original graph? Just in that case, think of incrementing the weight of that opposite direction edge by f of e. Or you could even think of adding a parallel edge. It's fine. Okay, you will always at most add 2 parallel edges. That's fine. So this is how you define the residual graph. Okay. So why did we do this? Right? So let's go back to this example. Okay. So now the claim is, if you find a path between S and T in this new graph, you can actually augment the original flow. Okay, that is the flow F. And the reason is, let's say I find this path. Note that this is the only path I can find, because intuitively these backward edges don't usually help, right? Because they're going in the opposite direction. You want to go from S to T, but these were kind of going in the backward direction. However, they help when you've made a mistake. For example, if I close this path, the reason this 28 is helping is because somehow in the optimal flow, you should have only used 10 of this edge. Okay, so let's say I find, so in this case I can find the flow of value 10, or so in this example, I find a path with flow equal to 10 in G sub F. Right, so in this case, this had a weight of 20. So I could have found this 10 here, 10 here, 10 there. And this is a path from S to T of value 10. Okay, of flow value 10. And this would be a valid flow in the residual graph, in this G sub F. So now the main observation is that, in some sense, if I call this flow F prime, so let F prime be the flow in the residual. then the claim is that f plus whatever that means, L f prime is a valid flow in G. Okay, and the plus here is what you would imagine. Okay, in the sense that if if the original flow f did not use this edge, then the plus is just a simple plus. Okay, so you just augment whatever f prime was sending on this. So let me define this. So this is an f plus f prime. So this is a sum of two flows, and I'm trying to define to you what does it mean to say a sum of two flows, right? So this is a new flow G. Okay, and remember, a flow is simply we have been viewing it as a sum of paths, but you could also view it as just a flow value on every edge, right? So this is a new flow for which the flow value on this E is defined to be f of E plus f prime of E, where f prime of E is treated as negative if it was on a backward. If it was on a, what do you call this? Yeah, backward edge. Okay, so what do we mean by this, right? So in this case, the new flow I would like to define is, so let me draw the two paths so that it's clear to you. So f was simply this 20, 20, f prime was a path that looked like this. Okay, f prime. Okay, and this had 10, 10. Well, this was using the backward edge E. Okay. And this was using the original edge. So this is f prime. Now, what we mean by the sum of these two is exactly what you would expect. So this plus this would be a flow that essentially looks like this. So it is, you get 20 here, and you have only 10 going down, because there was a 20 going down and there was a 10 going up. So you kind of add these together. Okay? And then there was a 10 here. And there was a 10 here, and there's a 20. Okay. Now note that this is exactly what our optimal flow was, right? So our optimal flow, which used paths 10 out here. Oh, I have chalk, I can probably do this. Yeah, 10 out here, and some math professors do this really well. I just I don't know how to do this. But, yeah, so you have 10 here, and you've got 10 here and 10 here, right? So this was the optimal flow. Okay, so yeah, and this is exactly what we have found. Okay, so f plus f prime is exactly. So there's a little bit of proof involved, but not much, in showing that G is always a valid flow in this. F plus f prime is a valid flow in G, right? So that claim involves a little bit more proof. what I've given is a proof somewhat by example, but yeah, let's not go too much into the detail. It's just using that fact, and you have to be a little bit careful about how you treat these negative edges, because the graph itself could have had edges in the opposite direction. In which case, you shouldn't be counting these things twice. So, especially when you're implementing these kind of things, it's always good to keep track of negative edges as like a separate array or something like this. Okay, so that you don't mess with existing backward edges. So this is, and thinking about it that way will also help you to prove. Okay, but we won't go into this, but we will accept this claim that f plus f prime, which I've defined like this, is a valid flow in G. Okay, and note that intuitively this flow f prime is correcting the mistake that you've made, right? So this residual graph has backward edges that allow you to correct for mistakes that you made. Yeah.
So I guess then I guess like how do you know when to stop? Then I guess you're gonna go like this. It seems like if you're just adding in negative edges each time, it's gonna be tricky to know when.
Right. So you stop when there is no more flows. Okay. So we stop. Right. Good point. I should mention that. Right. So we stop when we cannot add we cannot a path in G sub. Okay. So the algorithm is just as long as okay, so it's just like the initialization, so that I don't miss stuff. Okay, so this is called the Ford-Fulkerson algorithm. And it starts off with initialize f equals 0. This is your starting flow is just a zero flow, and at each step you find G sub f, and find path, which is actually called an augmenting path. Okay, so this is called an augmenting path. Which will drop the f prime, going from S to T in G sub f, okay. And you increment set f to f plus f prime, where f plus is defined like I did before, and repeat. And repeat until this find a path. Sorry. Finding a path in f prime step fails. And the question he asks is a relevant one. Why is it that this algorithm will eventually stop? Any thoughts on this?
Well, each time you find an augmenting path, you're increasing the flow, and since you're like modifying and increasing the flow, you're eventually going to get the maximum flow, which is you can't find any more augmenting paths that you're done.
Yeah. So what he's saying is exactly the right reasoning. He said so each time we are doing this incrementing of f plus f prime, the amount of flow you have going from S to T is only increasing. Okay? And it's strictly increasing because when you find the path, you found a path where every edge had weight at least one, something positive, right? So your total flow going from S to T is monotonically increasing in this process, and this is the reason it cannot go on forever, because it will have to eventually converge. And how long it takes is a very good question. So in your homework, so this is actually a very known standard example. In your homework, you will work out, I will give the example and you will work out why it takes a long time. Okay, so it depends on actually the weights of the edges themselves. Okay, so the amount of time it takes depends on edge weights. Okay, so if I specify the algorithm in such generality, where I just say find G sub f, find some path f prime going from S to T in G sub s, and so on, then the running time depends on it could depend on the edge weight. So there's a very simple modification of this algorithm, which I'll just mention without any proofs, where you find the shortest length path, which is the shortest number of hops path that goes from S to T in this step. I mean, if you're finding a path, you might as well find it using BFS or something. And that will have a running time that's only bounded by M and N. Okay, so it will be polynomial time. There's another way that you can do it here, which is called so when you always send the most amount of flow that is possible, pick some path f prime that has the largest value of the minimum flow on it. Okay, minimum edge weight on it. Okay, and that will also give a polynomial time, and these two vary slightly. So yeah, usually they're called fat pipes and short pipes. Okay, so if you think of these as like water pipes, the second algorithm I was telling you about is try to route a path, try to find an augmenting path that uses like fat pipes, where every pipe has diameter which is large, or every edge has capacity which is large. Okay, so yeah, so we won't go into that. So for now, yeah, so let's just say that you find any path. Okay, so this is enough for what I want to say. And the running time could depend on the actual edge weight. But the algorithm is very simple. Okay? So each time you have some flow f, you compute this residual graph G sub f, find a path which we call an augmenting path in G sub f. Okay? And let's call this path f prime. And you increment f to f plus f prime, where plus is defined like that. Okay, and you recur. Okay, so you keep doing this until you don't find an f prime line. And what he argued is that you always this algorithm has to stop, because in some sense you are always strictly increasing the amount of flow going from S to T. So you'll always have to converge.
What did the algorithm return?
Oh yes, the algorithm returns the f at the end. Return f at the end. Okay, so you do this until G sub f has no such path. Yeah. Return such and such and. Okay. Yeah, it's a good point. Okay, so this is what is called the four-filtration algorithm. So let me put this. I don't know if this is better or worse. Can you guys see the last line? Okay, yeah, return is the f at the end. Okay, so questions on this? Okay, so what is the let's go into, I've spoken a little bit about its running time, so let's go into why this algorithm is correct. Okay, so what do we have to show that this algorithm always outputs the right answer? Okay, what should be the formal claim? Given that we saw that the final f that it outputs is some f for which g sub f has no path going from s to p. Right? So that was the augmenting path we were trying to find. You stop only if there is no augmenting path. Yeah.
Maybe show that once it that the algorithm ends, like if and only if there are no more possible flows out of there that could be part of some optimal maximum flow, that you haven't excluded anything.
That's one way of showing it. But so that would be the how you prove this statement, right? But I guess the statement is clear. So the statement is just if f is the output flow, or rather, if f is some, so we will show the following. So if f is a flow such that g sub f has no s to t path, then f is the max. Okay, and you might want to prove it the way he's saying, right? So this is actually proof one, which we won't do. But one proof of this theorem goes by saying, let's look at the max flow. If it is larger than this f, then you can try to reason about the weights of the edges and try to show that there is at least one path that's remaining in G sub f. Okay, but it turns out that that is a rather messy proof. Okay, because you have to you don't know how this max flow looks like. You have to assume it is something and then slowly keep track of edges. Okay, so that's a very careful proof. So let's not do that. We will do a slick proof based on what I said earlier in the class. Okay, we will use this max flow min cut theorem to say that already this is starting to look like a cut version, right? So we are saying that in this G sub f there is no ST path. Okay? Now G sub f is not quite a graph in which we've just removed the sum of the edge weight. We have all these like weird backward edges. But this is already starting to look like the form we want. Okay, so we will use. So what we will do is prove optimality by demonstrating a cut whose value is equal to the value of the flow of f. Okay, so the proof idea is demonstrate a cut whose value, so the value of a cut is simply the sum of the weights of the edges in the cut. So the value is you can also call it value of f. So that's for a flow, the value is the amount of. And by what I said earlier, this implies that this is the maximum. So this is how we're going to show it. And proving this needs something about. Proving this is where we use the nice properties of this residual graph. So is what we want to show here. We want to demonstrate a cut whose value is. So I'm going to look at the residual. I'm going to look at G sub f. This will be some graph, so it will have some S, have some T. So it will have some S, it will have some backward edges, it might have some backward edges with this. It will, but what you know is that, oh yeah, and of course there's all edges, there's many edges right here. There's probably backward here. But what you know is that there's no edge that goes, or there might also be edges going like this. There is certainly no edge that goes all the way from S to T. Okay? Otherwise, there would be an augmenting path and you would increment f. So this is how G sub f looks like. Now, let's define Vs, okay, to be set of all u in the vertex set such that there exists a directed path and by this I mean a path that only uses positive edge weights, okay, using positive weight edges. That goes from S to U. In some sense, these are just the set of vertices that are reachable from reachable from S in this residual graph. Okay? This is all the vertices for which there is a path from S to that U. So like this vertex would be a part of V sub S. And maybe this vertex is not a part of V sub S because there is no directed path from S to this vertex, U prime. Okay. So what is one vertex that you know is present in V sub S? S, right, for sure. What is one vertex you know is not present in V sub S? You know T is not present in V sub S because you know there is no directed path. That's why you decided that this you decided to stop your argument. So, right, so we know that you know two basic facts. S belongs to V sub S and T does not belong. So the natural way to define a cut between S and T is, okay, you know, let's look at this V sub S, and this is some set of vertices. It includes S, doesn't include T. Okay. Let's try to reason what is, let's not, this was all in G sub F. Go back to G, okay, and try to reason about what is the value of the cut V sub, the cut which is the number of edges going between V sub S and the rest of the graph in G. Okay, so remember the max flow min cut theorem. We are always thinking about one graph, but this residual is just some helpful graph that you've constructed. Okay, so to exhibit a cut, you've got to exhibit a cut in the original graph, not in this G sub. So okay, so let's mimic this picture, but just the vertices this time, because the edges we know are all messed up. The edges here are a little bit different. In G are a little bit different. So let's look at G. But now the vertices are all you have. So it's maybe tough for me to do without actually seeing. So there's, and these are the vertices in V sub S, and these are the rest. Now in G, I want to reason about what are the total edges that go from V sub S to this other set. Okay, so let's call this V sub T just for, just V sub S complement. This is the rest of the vertices, right? So I want to think about the following quantity, which is what is the total weight of edges from V sub S to, it's a directed edges, right? From V sub S going to V sub S complement.
Greater than the mean cut.
It is bigger than or equal to mean cut, sure. Can you talk about this in terms of the flow? Okay. In terms of this flow S. Right? Remember, V sub S was constructed using this residual which depended on F. So, what I would like to show is that the total weight of edges going from V sub S to this V sub S complement is, let's write bar, complement, is exactly the value of the flow. This is what I would like to claim. And if I claim this, I am happy because then it shows that there was a cut in the original graph whose value was equal to the value of F. And then, by what I have shown earlier, this was the optimal. Okay. So this is what we would like to say. Okay. So is this clear? What I would like to say? Alright. So now let's see how to show this, right? And for showing this, think about it a little bit. This is not so complicated because, so abstractly, if I had any flow, okay, which went from S to T, and I had some flow that went like this, so on. Okay. And I gave you some set that included these guys. What would be one way to compute what would be one way to say what is the flow value of that goes to this? Okay, so I'm calling this vertex set just some V prime. Okay, so this is a bunch of vertices. If you want to take a very simple example, maybe this picture is confusing, but if I had a flow where you had S and T here, and I gave you some set of vertices like this, and suppose these were all unit flows. Okay, maybe just to be 2, 1, 1, 1. Okay, 2, 1. Suppose this is some flow where I just came out of it. Now I ask you, what is one way to compute the value of this flow? I want to claim that if I take any set that contains S and look at the net outward flow from that set, it's going to give me the value of the flow going from S to T. Okay, in this case, what are all the edges that go out from that are like this? I have this edge, or this edge. Okay, these are the edges that go from this set of vertices outside. Okay. And what is the net outward flow? You've got 2 minus 1, because there's an inward flow, plus 2, which is 3. Okay, and this is the value of the flow that goes from S. This is a very physicsy way of thinking about this, right? Because it's like, I don't know, what is this theorem called? In electromagnetism, there's all these things about the net outward flow, divergence or something, it's called, right? And you have the surface integrals of the divergence is equal to the net outward flow, the flux. These things don't sound familiar. Sorry? Yeah. It's one of these Maxwell's theorems. Yeah. So, but this is a very and this basically follows from the fact that S is the only source, and T is the only place where S and T are the only places where flow conservation is not satisfied. For any other vertex, net inflow is equal to the net outflow. Okay, so if you sum these things, you get what I said. Okay, so it's a very similar reasoning. Okay, that if I take any set of nodes that includes S, okay, the net outward flow will be equal to the value of the flow from S to T. And if I take any set of nodes that does not include either S or T, okay, so it doesn't include either S or T, then the net outward flow will be 0. Yeah, everything that goes in has to come out. Okay, because the only vertices for which flow conservation is not satisfied are S and T. And if I take things that include both S and T, it's again 0. So this is a very simple fact. Okay, and now you can use this fact, it turns out, maybe you don't have time, but you can use this fact to argue that in G, if I looked at the net outward flow, so then this would clearly be equal to the value of F. Okay, so outward flow in F. Right? But now you have to argue what about this edges that go back. Okay, and now I want to claim that this flow F could not have used any edges that went back from outside of V sub S into V sub S. And the reason for this is that if in G, F had used the path that went back, then the backward edge corresponding to this edge would have actually gone outside. Okay, which means that in G sub F, there would have been a path that went out like this. Okay, and this can happen because G sub F was that this Vs was defined as a cut in some sense in this. Okay. So this is a very cool proof. So I will point a link to this because we're out of time. I think if we had the slides, I could have gone faster. But this is the rough idea.